The pedal hit the floor and stayed there, a fully loaded rig on a 7% grade, brake drums glowing cherry red, and the smell of scorched lining rising through the cab. The air system still had pressure, and the pedal still moved, but the friction was disappearing, and the bottom was still 3 miles away. This is the engineering history of brake fade. What it actually was, why drum brake physics made it inevitable on sustained grades, and how a compression release mechanism developed in the late 1950s rewired the fundamental energy equation of a loaded Class 8 descent. The Jake brake didn't improve drum brakes. It dramatically reduced how often the service brakes had to be used on the downgrade. To understand what fade destroyed, you have to understand what a drum brake was actually doing under load. The system is deceptively simple in schematic form. A cast iron drum, bolted to the wheel hub, rotates with the wheel, and inside it, a set of curved brake shoes lined with friction composite are forced outward until they press against the drum's inner surface. On heavy trucks of the 1940s and 50s, that force usually came through an air-actuated system. An engine-driven compressor filled reservoirs with compressed air. The driver's pedal sent that pressure to brake chambers at the axles, and the chambers moved pushrods that turned S-cams, forcing the shoes outward against the inside of the drum. It was strong, serviceable, and well-suited to normal freight work. The limitation was not stopping power. The limitation was heat. Kinetic energy, the product of mass and velocity, transferred into the shoe drum interface as heat. The drum absorbed that heat and, ideally, radiated it to the surrounding air. The failure mode begins with the friction material itself. Brake linings in the 1950s and early 60s often used asbestos-based friction materials bonded with resin, though formulations varied by manufacturer and application. These materials were engineered with a friction coefficient in the range of 0.35 to 0.45 under cold or moderate temperatures. Enough grip to generate serious retarding force from modest actuation pressure. The problem was thermal degradation. As temperatures climbed, the resin binder and friction materials could begin to break down, causing the lining to lose grip. The organic compounds in the lining vaporized and formed a thin gaseous layer between the lining surface and the drum. That gas layer acted as a lubricant. Friction coefficient collapsed, in severe cases dropping below 0.15. The driver pressed harder, generated more heat, accelerated the volatilization, and reduced friction further. The system chased its own failure in a closed loop. Drum brakes dominated heavy trucking because they were compact, enclosed, mechanically simple, and capable of producing enormous braking torque for their size. They also had a self-energizing effect. As the shoe contacted the rotating drum, the drum's motion helped pull the leading shoe harder into the braking surface. That made drums powerful and practical for heavy vehicles long before large disc brakes became common. On flat roads, that trade-off was manageable. On a mountain descent, it became the system's central weakness. Cast iron drums compounded the problem through thermal expansion. A 16.5-inch drum, the standard diameter for rear tandem axles on heavy trucks of that era, would expand radially as it heated. As the drum heated up, it expanded enough to increase shoe-to-drum clearance and reduce braking response. That thermal growth increased shoe-to-drum clearance, so the shoes had to travel farther before full contact and braking effect was delayed. On S-cam air brake systems, the slack adjuster geometry was calibrated for cold drum dimensions. At high temperatures, drivers were simultaneously losing friction coefficient and losing mechanical leverage, a compounding deficit that standard slack adjustment could not compensate for in real time. The mountain grades on major western freight routes made brake fade a recurring danger rather than a rare exception. Major Colorado mountain grades could reach 6 to 7% on long descents. U.S. Route 40 over Donner Pass in California runs sustained grades between 5 and 7% for stretches exceeding 10 miles. Appalachian descents on major highways also presented long, demanding grades for loaded trucks. A loaded 80,000-pound combination vehicle descending a 7% grade for 5 miles generates a gravitational force component along the slope of approximately 5,600 pounds of continuous push. The drum brakes on a 3-axle tractor-trailer of 1955, a Peterbilt 350, a White 3000, an International DCO 405, were not engineered to absorb and dissipate that energy continuously. They were engineered to stop the vehicle from highway speed in an emergency, a fundamentally different thermal load profile. The industry's institutional acknowledgement of this limitation was the runaway truck ramp, gravel escape lanes cut into the hillside on the worst descents at intervals calculated to catch a vehicle that had lost braking control. Runaway truck ramps were developed as a response to repeated brake failures on steep grades, especially in the West. Their existence was not incidental. They were engineered infrastructure built around the accepted probability that drum brake fade on loaded trucks was a recurring, predictable event rather than an anomaly. Under those conditions, adjustment, balance, and driver technique became critical. One axle slightly out of adjustment could force the others to do more work. A trailer with hotter drums could begin fading before the tractor. The whole combination depended on cool brakes, proper gear selection, and a driver disciplined enough not to drag the pedal. That was the gap the Jake brake would eventually fill. It did not make the old drum brakes stronger. It reduced how often they had to be used. By the time the compression release brake moved from concept to patent, Clessie Lyle Cummins had been circling the same problem for years. A diesel engine could pull a truck with extraordinary efficiency, but on the downgrade, it gave almost nothing back to the driver. Cummins had founded his Columbus, Indiana engine company in 1919, and his engineering instinct was direct. He observed mechanical problems in terms of energy and tried to find the simplest possible pathway for that energy to go somewhere useful, or at least somewhere harmless. The diesel engine's braking deficit bothered him on a fundamental level. A gasoline engine develops meaningful compression braking because a closed throttle plate generates high manifold vacuum on the intake stroke, resisting piston movement. A diesel has no throttle plate. Fuel cutoff stops combustion, but leaves the engine spinning freely against only its own mechanical and pumping friction, an insignificant retarding force on a loaded vehicle. The compression release concept Cummins developed inverted the engine's normal energy conversion. In standard operation, a diesel piston compresses air in the cylinder to roughly 16:1 to 22:1 compression ratio, depending on the engine design, raising air temperature above the auto ignition's point of injected fuel. That compressed charge then drives the piston downward on the power stroke, doing work. Cummins recognized that the compression stroke itself represented a substantial energy expenditure by the drivetrain. If the compressed air could be vented at or near top dead center, before it could expand back down and return energy to the piston, that entire compression event became a net energy drain rather than a net energy source. Multiply that drain across all 6 cylinders of an inline 6-cylinder diesel firing at engine speed, and the braking horsepower is significant. The mechanical challenge was actuating an exhaust valve opening at precisely the right crank angle, ideally within a few degrees of top dead center on the compression stroke, without disrupting normal engine operation when the system was not in use. Cummins developed the concept, and Jacobs Vehicle Systems commercialized it in 1961. Jacobs later received a U.S. patent issued in 1965, and the brake was commercially available by 1961. The physical architecture of the Jacobs engine brake, as developed for the Cummins NH series engine, the 855 cubic inch inline 6 that was the dominant displacement in long-haul trucking through the 1960s and 70s, works as follows. A control valve mounted to the rocker arm cover housing contains a solenoid-actuated oil control valve that, when the cab switch is closed and oil pressure from the engine's lubrication circuit is present, opens the hydraulic circuit to the brake mechanism. Each cylinder has a master piston assembly positioned to contact the fuel injector rocker arm. As the injector rocker arm rotates through its cam-driven travel toward the fuel injection event, which on a 4-stroke diesel occurs near top dead center of the compression stroke, it depresses the master piston. The master piston displaces hydraulic oil through a calibrated passage into the slave piston circuit. The slave piston, positioned directly above the exhaust valve crosshead, is forced downward by this hydraulic pressure, opening the exhaust valve by approximately 0.015 to 0.020 inches. This small opening is sufficient to vent the compressed air charge. The compressed air, rather than returning energy to the piston on the expansion stroke, exits through the exhaust system. The cylinder that just spent crankshaft energy compressing a full charge to 500 to 600 pounds per square inch returns nothing to the drivetrain. On a downhill run, the Jacobs brake repeatedly vents compressed air from each cylinder at the proper point in the cycle, converting engine compression work into retarding force. The system could produce substantial retarding horsepower at higher engine speeds, enough to keep the service brakes cool on long descents. At 1,500 revolutions per minute, usable retarding force was in the range of 180 to 220 horsepower, depending on manifold pressure and specific engine calibration. Those numbers translated directly into driver experience. In the right gear, a properly equipped truck could often hold speed on a 6% grade with little or no service brake use. The drum brakes remained cold. Brake lining temperature stayed within normal operating range. The failure cascade, thermal expansion, resin volatilization, friction coefficient collapse, never initiated because the thermal load that triggered it was never applied. Jacobs brake systems were also offered on some Detroit diesel engines, along with Cummins and later Caterpillar applications. Caterpillar's 3406 family received compatible Jacobs units as that engine became a significant market presence through the late 70s and into the 80s. The device, because it was an add-on assembly requiring no internal engine modification on early applications, bolting to the rocker cover, mounting surface, and tapping into existing oil galleries, could be dealer-installed or shop-installed on engines already in service. List pricing for a complete 3-unit installation on an NH855 in the mid-60s was in the range of $600 to $800. A figure that fleet operators running mountain routes recovered in reduced brake reline intervals within a single annual maintenance cycle. The regulatory collision came from a direction the engineers at Jacobs had not engineered against: sound. The compression release event, cycling through 6 cylinders at operating RPM with the exhaust valve briefly opened, produces a sharp staccato report through the exhaust system. On a pre-emission Cummins NT C855 with open exhaust or minimal muffling, the Jake brake operating at 1,800 RPM on a long downgrade produced measured sound pressure levels in the range of 85 to 92 decibels at 50 feet. The sound was sharp and distinctive, and it quickly became one of the most recognizable noises in trucking. By the mid-70s, municipalities along interstate corridors began adopting local ordinances restricting engine brake use. Many towns near steep grades responded to noise complaints by adopting local restrictions on engine brake use. Fine structures varied. Some ordinances set penalties at $50 to $100 for a first violation, others as high as $250. The no engine brake signage became standard infrastructure on approaches to hundreds of towns from Pennsylvania to California through the 70s and 80s. The Federal Highway Administration did not preempt these local ordinances. The Noise Control Act of 1972 created federal authority over motor vehicle noise standards, while local jurisdictions still retained some authority over vehicle operation within their borders. The result was a patchwork of restrictions that varied street by street in some corridors, creating operational complexity for drivers who needed to manage brake system heat on the very grades where local law prohibited their primary retarding tool. The deeper structural shift arrived not from noise ordinances, but from emissions architecture. EPA heavy-duty diesel emissions standards and the 1998 engine manufacturer settlement accelerated the shift toward electronic engine controls and cleaner combustion strategies. Achieving the NOx and particulate matter thresholds in the 2002 and 2007 standards required electronic fuel management, exhaust gas recirculation, and ultimately after-treatment systems, including diesel particulate filters and selective catalytic reduction. The high compression ratios and long injection durations of the mechanical engines were no longer compatible with emissions targets. Compression ratios on new heavy diesel engines were reduced in some applications. Combustion chamber geometry was revised. The operating characteristics that had made the original Jacobs brake so effective, the predictable, high-compression mechanical injection event providing a consistent master piston actuation signal, were replaced by electronically controlled, variable duration injection events managed by engine control modules, Jacobs Manufacturing, by then a subsidiary of Danaher Corporation, adapted the brake architecture accordingly. By the late 90s and into the electronic engine era, some Jacobs brake systems used electronic controls instead of a purely mechanical trigger. Electronic integration with the ECM allowed the brake to be triggered by a software signal, with hydraulic actuation timing controlled by the engine management system rather than by physical contact geometry. This preserved compression-release braking through the transition to electronic engines, but added a dependency layer. A Jacobs brake on a 2007 compliant Cummins ISX or Detroit D15 required compatible ECM calibration, software enablement by the OEM, and integration with the vehicle's J1939 databus. Some modern Jacobs brake systems required electronic calibration and diagnostic access in addition to mechanical service. The 1998 consent decree itself, formerly the Settlement of United States versus Engine Manufacturers, required the 6 manufacturers to pay a combined $83.4 million in civil penalties and commit to approximately $850 million in emissions-related research and retrofitting expenditures. It accelerated the electronic transition by a measurable margin, forcing engines into compliance windows that compressed the development timeline for the next generation of powertrain electronics. On some modern trucks, engine brake operation may be limited during diesel particulate filter regeneration to help the aftertreatment system maintain the temperatures it needs. The Jacobs engine brake remains in production. The current product line covers several major heavy-duty engine families used in North American trucking. The fundamental physics: vent the compressed charge near top dead center, extract the compression work from the drivetrain, dissipate nothing through the wheel brakes, has not changed since its original patent. Runaway ramps still exist on major mountain grades in Colorado and California, where they are designed to stop vehicles that have lost braking control.